Yes. Uh, Good evening to all, and welcome to the another session of the live interactive section of the NPTEL course Heat Transfer. This is our fourth session, which we will be discussing some of the questions related to the week four topics. So let's have a brief recap about what are the things that are discussed in the week four. So till week three, we were discussing about the one mode of heat transfer, which was conduction. So in week four starts with the next mode of heat transfer, which is a convection. So where the bulk fluid motion is involved. So in the initial lectures of fourth week, so the basics of fundamentals of convections were discussed. Then the flow over a flat plate and like boundary layer, the temperature profile and the velocity profile, etc., of a flat plate when there is a flow over a flat plate happening that we discussed. So so now we will start with some of the questions that are related to these topics. Some simple questions. Okay. So because in week four it was not just the fundamentals of the convections were discussed. So in the coming weeks, uh, we will we will go deep into the convection topic. So first we will start with the first question. So we will follow the same pattern. I will give you some time to solve the problem. After that, I will uh, solve it for you. Okay, so this is the first problem. The coolant flows at 30 degrees Celsius over a heated flat plate maintained at a constant temperature of 100 degrees Celsius. So the boundary layer temperature distribution, the temperature distribution within the boundary layer is given. Okay, and the thermal conductivity of the fluid is also given. And we have to find out the local convective heat transfer coefficient at this location where this temperature distribution is given. Okay, so this is our question. So we have to find out the local heat transfer coefficient. So I will give you some time to solve. So did you got the answer?
No, sir.
Yeah. Okay. So I will solve. So we are given with the temperature profile. Okay. And the thermal conductivity of the fluid is also given. So what is the definition of means heat transfer coefficient H? is already discussed in the class, that is minus kf dt by dy at y is equal to 0 divided by t surface minus t infinity. Okay, so just substitute these values because dt by dy we know already the temperature profile is given, so which is how much, 70 into e raised to minus y into minus 1, so that is minus 70 e raised to minus y. Okay, so what is the temperature profile at y is equal to 0? So just put y is equal to 0 in this equation, so it is minus 70. Okay, now h is equal to minus kf dou t by dou y at y is equal to 0 divided by ts minus t infinity. Kf is already given, is 1. This dou t by dou y at y is equal to 0 we found out minus 70. Then ts minus ts surface temperature is given, that is 100, and t infinity, that is the fluid temperature, is given. So what is this answer? It's 70 by 70, which is 1 watt per meter square Kelvin.
Sir, isn't it the overall convection coefficient?
No, actually, uh, so this can be the temperature distribution at a particular location. So we may not be true that this is a temperature distribution all along the boundary layer. Okay, that's why it is called as a local heat transfer coefficient. At that particular location, we are finding out where this is the temperature distribution. This is not the uh, entire heat transfer coefficient. This is the local.
Okay, sir.
Okay, let's move on to the next question. In this question, we have an oil flow in a journal bearing, which can be treated as a parallel flow between two isothermal plates, with one plate moving at a constant velocity of 12 meters per second and other stationary. So this is like a flow over a flat plate, sorry, flow between two flat plates. So this lower plate is stationary and the upper plate is moving with a velocity of 12 meters per second. So consider such that a flow with a uniform spacing. So this the distance between the plates is 0.7 mm. Okay, and the temperature of the upper plate is 40 degrees Celsius, where that is at the lower plate is 15 degrees Celsius. So determine the velocity and temperature profiles. That is our first question. You may please try. It's like a flow over a flat plate. Sorry, flow between two parallel plates.
Sir, that temperature is quadratic function of y. So then, how we will write that quadratic equation?
What? No, I just at last I want the function, means temperature. What is the function of temperature with respect to y? That we have to find out. the temperature and velocity profiles. So we can start with for velocity profile, you can start with the Navier-Stokes equation, and you can neglect the terms that are not applicable for this case. And so this will lead to the velocity profile. And for temperature profile, you have to write down the energy equation, and you have to neglect the terms that are not applicable. That will lead to the temperature profile.
Sir, isn't there any equation for Kuwait fluid that can be
Yeah,
directly?
actually, from the governing equations, you can find it out. Like fluid flow, it's like a shear driven flow. The flow is happening because of the movement of the top plate. So it's called a shear driven flow. There is no applied pressure. So you can take the pressure gradient in the Navier-Stokes equation at zero. Like that, if you can reduce the Navier-Stokes equation, and you will get the velocity profile. So so let's the u component of u component of x component of velocity I'm taking is as u, and the y component of velocity as v. Okay. So as it is a parallel flow, we can consider the v component of velocity as zero. Okay. So only the u component of velocity, which is along the x direction, is there. So use this as an input to the what to say 2D. You can this is a 2D problem. You can assume it as a 2D problem. So write the continuity equation. You will get some uh, input from that, and use that input to the uh, x direction, x momentum equation, or the Navier-Stokes equation in x direction. So then cancel out the terms that are not required. Finally, we will arrive at a velocity profile. So what is a continuity equation?
Currently, that dou u by dou x
Yeah, it's a 2D. So dou u by dou x plus dou
plus
v by
dou
dou
u
y
by dou y.
equal to 0. Am I right?
Yes.
So as v is equal to 0, this component is 0, right? So what we get is dou u by dou x is equal to 0, which means u is not a function of x. So u is a function of y only. Okay. So this is the information we get from what continued equation. Am I right?
But sir, is that we considering the flow is steady?
Yeah, you can assume steady flow. I have not mentioned, right? Okay, you can assume steady. So u is a function of y only. So that is the insight we get from the continuity equation. What is the x momentum equation? Rho times dou u by dou t plus u dou u by dou x plus v dou u by dou y is equal to minus dou p by dou x plus rho gx plus mu times dou square u by dou x square plus dou square u by dou y square. Am I right?
Yes, sir. Sir,
Yeah.
actually, if the flow is steady,
Mm.
then it means we are writing this equation within the boundary layer, not outside the boundary.
No, here I'm not saying about anything about boundary layer.
Because my confusion is that if if that we are considering as it to be a steady state, then even curly u by curly x should also be zero if it is outside the boundary layer.
Which one? Which one?
That dou u by dou x.
No, I have not applied anything. I'm just writing the exponent equation. That's all. I have not applied to this case. This
Okay.
is the exponential equation in 2D. So I just write it. This is general equation. So now I am applying it. So when it is steady state, the first term is 0. Okay. There is no applied pressure gradient. So this term is 0. There is gravitational forces I am neglecting. This is 0. And dou u by dou x is 0. V is 0. So this term is 0. And dou u by dou x is also 0. So what we end is d square u by dy square is equal to 0. I think your confusion is there is no confusion now. Okay. So can you please integrate this and say what is the velocity profile?
It will be straight line with intercept.
Yeah. So u will be c1y plus c2. Okay. So if you apply the boundary conditions at y is equal to 0. So I'm taking this as xy. Y is equal to 0. That is u is equal to that is u at y is equal to 0. So the bottom plate is stationary. So at y is equal to 0 to satisfy no slip condition. What should be the u? You are not understand the problem. What
Y.
is, yeah, at y is equal to 0 means this is my coordinate axis. At y is equal to 0, what is u?
Sir, U is 0.
Yes, because it's a stationary, which gives C2 is equal to 0. Okay. At y is equal to L means the gap. What is u?
The velocity with which the plate is moving.
Yeah, v. So v is equal to C1 L, which gives C1 is equal to v by L. So what is the velocity profile? U is equal to v by L times y. You just check whether this is satisfying. At y is equal to 0, u is 0, and at y is equal to L, u is equal to v. So this is a linear profile. So our first part of the question is over. Our second part is to find out the temperature distribution. So as the this is a frictional means it's a oil, right? Oil, and this has a very high right viscosity, especially while dealing with oil. Unless it is specified, we cannot neglect the frictional heating due to viscous dissipation because of the high viscosity of the oil. So in some cases, in some questions, in order to reduce the uh, computation, it will be given frictional heating or the viscous dissipation can be neglected. But if it is not neglected, you have to consider the frictional viscous dissipation effect also while dealing with high viscous fluids like oil, oil like that. Okay, so if you write the energy equation in two dimension, so you will get rho Cp u dot t by dot t by dou x plus v dot t by dou y should be equal to k times dou square t by dou x square plus dou square t by dou y square plus mu phi. So this mu phi is the viscous dissipation term where phi is equal to, so already about this the so this phi is equal to, we can write 2 dou u by dou x the whole square plus dou v by dou y the whole square plus dou u by dou y plus dou v by dou x whole square. Okay. Now we are cancelling out the non-important terms. So as the plates are isothermal and there is no change in the flow direction, the temperature depends only on the y, means the temperature will not be a function of x. Okay. So and as there is a steady state, there is no need of considering time. So if you apply this here, dou t by dou x will be 0. Okay, v is equal to 0, so the second term is also 0. So dou t by dou x will be 0. And if you go here, dou u by dou dou u by dou x is 0 from the continuity equation. V is equal to 0 and dou u by dou v by dou x is equal to 0. So if so this will lead to the equation 0 is equal to k d square t by dy square plus mu times du by dy the whole square. So this is the energy equation. So from that you will get d square divided by dy square is equal to minus mu by k du by dy the whole square. Okay. So what is du by dy? We already found out the temperature, sorry, velocity profile. What is du by dy?
V by L.
Yeah, it's V by L. So we substitute here. So du by dy is equal to V by L. So which becomes minus mu by k V square by L square. So so if you differentiate it, sorry, if you integrate it, what will be t of y minus mu by k du by dy, sorry, minus mu by k V square by L square into y square by 2 plus C1y plus C2. So this is the temperature profile. Okay. So the so if you can put the boundary conditions and find out the constants C1 and C2. Okay, because at y is equal to 0 and y is equal to L, the surface temperatures of the plates are given. So you can find out the constants C1 and C2. So the temperature is a quadratic function of y, and the uh, but velocity is a linear function of y. So that is our conclusion. So now next is same problem. It's a continuation. We have to determine the maximum temperature and location where it occurs. Okay, so for that we have to find out C1 and C2. So I am taking this equation and once again mu by k v square by L square y square by 2 plus C1y plus C2. So at y is equal to 0, what is the temperature? It's 15 degrees. Okay. So, so if you find out 15 is equal to this become can C2. And at y is equal to L, what is the temperature? What is the temperature of the upper plate?
It is
Otherwise,
50, 50.
no. What I will do is I will just write it in the general terms because uh, so that you just need to substitute the values. So let it be, let the so let the lower plate be at T1 and upper plate be at T2. Okay. So just I am generalizing the equation. So at y is equal to 0, it's T1. So C1 is equal to T1. Okay. Here in this case, it's 15 degree, that's all. But I'm writing this in general form. So at y is equal to L, T is equal to T2. So T2 is equal to minus mu by K V square by L square by 2 plus C1 is what? C1L, sorry, it's not C1, it's C2. Okay. C2 plus C1L plus C2. C2 is T1. Okay. So what is C1? C1 is T2 minus T1 by L plus mu by K V square by 2. So if you divide throughout by L, L is equal to C1. Am I right? This is the value of C1. Okay. So C1 is equal to T2 minus T1 by L plus mu by K T square by 2L. If you substitute these constants back, you will get T of Y as minus mu by 2K V square by L square into pi square plus T2 by T1, T2 minus T1 by L times Y plus T1. Okay, so if I'm just rewriting it, you will get mu V square divided by 2K L square. I forgot one. I missed one time here. Yeah. Plus mu by K V square by 2L times Y plus T1. So it becomes YL minus Y square because I am combining this term and this term plus T2 minus T1 by L times Y plus T1. So this is the temperature profile without constants. So when we solve the constants C1 and C2. Now we can start the our this question, this third question. So when we how to determine the maximum temperature? We are given with the temperature profile. So how to determine at what location the maximum temperature is happening, and also it's what is the value of that?
So dt by dy should be 0.
Yeah. So first we will differentiate this dt by dy. So can you please do, because everything I have given. So can you please differentiate and just say the expression for y? So I will wait for 2-3 minutes. So just differentiate this equation with respect to y and let me know what is the expression you are getting. And also, in fact, you can okay. I'm so you can take the velocity, means the properties of the oil. So because you need mu and all. K is 0.145 watt per meter Kelvin, and mu is equal to 0.580 Newton second per meter square. You can consider this property. So just everything is given. So check, just differentiate dt by dy is equal to 0, and you will get an expression for y. Okay. So in the y expression, you just substitute t2, which is in this case it is 40. How much it is 40 and 40 40 40 and T1, which is 15 degrees. So, and L is already given 0.7 mm, and the mu and K value I have given now. So you can just substitute this value and find out what is the value for Y, where the maximum temperature happens.
So how much is the L? Can you just show the statement?
This one or the question?
Question, sir. What we will take L, how, that what is L? Capital L.
L is the distance between the plates. I already mentioned.
Okay, okay.
Are you getting the answer? So okay, I will also start doing. So you please cross check. Okay. So it is by dy is equal to if you differentiate mu v square divided by 2k L square times L minus 2y plus t2 minus t1 by L. So t1 becomes 0. So this becomes 0. So if you write mu L square divided by 2kl mu v square minus mu v square y by kl square plus t2 minus t1 by L is equal to 0. So if you rearrange this and if you take the y is equal to, you will get it as y is equal to somewhat, some rearrangement is required. So it's L times 1 by 2 plus k t2 minus t1 divided by mu v square. Are you getting up to this? Is your answer correct?
Yes, sir.
Yeah. Okay. This for arriving this step, you needs two three more simplification steps. So I'm not doing that. I think you can get arrive at this location.
Yeah, I did it, sir.
So you got this answer, no?
Yeah.
Why? Okay. So now just can you please substitute but L is equal to zero point 0.7 mm. So you have to convert it into meters. Okay. K is already given 0.145 watt per meter Kelvin and mu is equal to 0.580 Newton second per meter square. So can you please calculate this? And T2 is equal to 40, T1 is equal to 15.
What about V?
V is already given 12 meter per second.
Actually, sir, I got it 3.5 into 10 to the power minus 4.
3.5. Okay, 3.5 into 10 raised to minus 4 means or 0.35 mm.
Yes.
Yeah, okay. So I'm getting around 0.38. Okay, fine. So, 0.35 mm. Okay, so that's the answer. So that at this location, the T max, the temperature is maximum. And and you are asked to find out the maximum temperature also. How to find out the maximum temperature? T max. We are given with or we find out the location for where the maximum temperature happens. So how to find out maximum temperature then?
So in the expression of Ty, we will put y equal to 0.35.
Yeah. So just please do that and let me go and answer. got the answer?
I'm just calculating, sir.
Okay. So you can also try d square t by dy square because you don't know whether it is a point of maximum or minimum. So you can check. Yeah, I'm giving this as a homework. So it should be so that second derivative when you put this value it should be less than zero. Then only we can uh, guaranteely say that it's a maximum. Okay, it should come as negative. So you can try try it as a homework. Okay, so you can check if it is somewhat near to 100 degrees Celsius. Okay, so you can just verify this answer. So can we move to the next question? It's just uh,
Okay, sir.
substitution of the value. So you
Yeah,
can
yeah. Okay,
take
okay.
and take your own time. Yeah, next question is also a continuation. So you have to determine the heat flux at each plate. How to find out the heat flux? What is the formula for heat flux? Q is equal to minus
KF,
K
KF.
F. Okay, dou T by dou Y at
Yeah,
that location, right? Where we need to find out. So at Y is equal to 0, if we put, we will get the heat flux at lower plate or upper plate. Because what I am specifying is you can take your own sign convention. Means you can take your own coordinate system. So this is not necessary that you need to fix the origin at Y. You can fix at the middle. But always you should remember that uh, it's always preferred to take or means fix the coordinate which we will get, which is easy to simplify. So you can fix the coordinate the middle also. If you fix coordinate the middle, what happens is this may not be zero. At y is equal to zero, u is not zero, right? So
yeah.
it will make some more calculation intensive, but you will finally arrive at the same almost same. I'm not saying this velocity profile, but you will get a linear velocity profile. So it's always uh, you should fix the origin very carefully. Okay, so at y is equal to zero, I am taking which is my lower plate. The heat flux, I will get heat flux at lower plate. Okay, so the temperature profile I already know what is T of y is equal to what is my temperature profile. Mu v square divided by 2 kl square yl minus y square plus t2 minus t1 by l times y plus t1. Okay, so q at lower plate equal to minus kf for the fluid times what is the derivative at y is equal to 0 mu v square divided by 2 kl square. If we
I,
differentiate this,
sir, we have already done it, I think.
Yeah, we already done this one, right? So
Yes,
if we put y is equal to 0, you will get mu v square divided by 2kl, right? 2kl, then plus t2 minus t1
by M.
by l. So if you calculate this, so you can just, it's just a calculation. So you will get approximately minus 448464835.71 watt per meter square. Okay, because I'm not spending time on this calculation because every values is already given. Okay, so I think you can do it by yourself. So next, Q at upper plate minus k dou t by dou y, or we can write, even write dt by dy because t is function of only y. Okay, dt by dy at y is equal to, what is the location of upper plate?
So, L
Yeah,
equal to L.
at here. Okay, so if you, we already found this out, so we already have the, yeah, this one. So at L, what is this value? L minus 2y, right? So L minus 2L. So it will become minus L. So minus mu v square divided by 2kl plus t2 minus t1 by y. So, so you will get answer as 5.45 into 10 raised to 4 watt per meter square. Okay, so this is also means the values are already given. Just substitution is necessary. So these are the heat flux at the lower and the upper plates. Okay, so this was a little bit lengthy
Sir,
question. So I
this,
split.
sir,
Yeah,
this in our last equation, won't it be
which
T2
one?
minus T1 here? This one, last term will be T2 minus T1 only.
By L. Yeah,
But why we are putting L now?
yeah. This is not there. This is the, you see. This is already there. Na? T2 minus T1. It's by L. We already differentiated it, and that term doesn't have y.
Okay, okay,
This
okay,
term.
sir. Okay, okay.
So this was a little bit lengthy question. So I just split it into uh, parts, three, four questions. So a similar kind of question can be also asked where both the temperature, both the plates are at same temperature, or both the plates are stationary with a pressure gradient like that. So accordingly, it's like a fluid mechanics problem. So the heat transfer only comes when we are using energy equation. So basically, we should start with the fluid mechanics problem because, okay, because we need to find out the temperature profiles and, oh, sorry, the velocity profiles to find out the, to get the temperature profile. So I hope you have studied this kind of laws in the fluid mechanics, so which will be useful here to solve this kind of questions. So we are moving to the next question. This is a simple question, so I hope you can able to solve this. So we have a experimental results of a local heat transfer coefficient Hx over a flat plate by using some experiments and by fitting some correlation. So this is the expression I got by experiment for a local heat transfer coefficient for a flow over a flat plate. So I would like to get determine the ratio of the average heat transfer coefficient divided by this local heat transfer coefficient. Can you please try? This is a simple question. I will wait for 2 minutes. So after that I will solve because, so the expression for the average heat transfer coefficient was already discussed in the class. So I just just the mathematics part of it.
So I am able to solve it, but I am not getting the correct option.
Okay, I will solve. So, what is the expression for average heat transfer curve
So
at
I
any
have
location x? Means up to,
1 by x
yeah,
integral 0 to L,
okay, 0 to L or x means up to whatever the length I am taking. Okay, so I'm just taking it as x.
then hx local dx.
Yeah, dx. So, so here, uh, 1 by x equals 0 to x. What is hx value? A raised a into x raised to minus 1 minus 0.01 dx. Am I right?
Yes,
So, so a is a constant, so I am taking out integration. So x raised to minus zero point 0.1 is integration x to 0. Is it right? So h bar x is equal to a by x.
sir. Before integration, we have to take x also inside, na?
No, no, not required. The x is not in. Uh, the x is outside integration.
So we should not take it inside.
No, no, no.
Okay.
No need of taking inside. It's like we are averaging over the x, right? So how this came? Like we are taking. So we are taking an elemental strip and we are calculating the, and we know the h at that location, right? And we are what we are doing is we are assuming the depth which is into the plane of the paper as one. So integral 0 to s hx into the area which is dA. So what is dA here? It's a flat plate. So the dx which is the elemental length into the one. So that's how this part came. This is the average heat transfer coefficient. Okay. So this is hx bar into x up to that length into 1. So we are bringing this down. That's all. Okay. I hope it is clear now.
Yes, sir.
Yeah. So now I think you can solve this. So you will get minus sorry 0.1 divided by 0.9 x to 0, which is equal to a by x raised to zero point 0.9 by zero point 0.9. So which is equal to x bar x is equal to a by, I am cancelling that x, zero point 0.9 x raised to minus zero point 0.1. Okay, what is this? A x raised to minus zero point 0.1. This is the local hx by, right? So the required ratio is h bar x divided by hx, which is equal to 1 by zero point 0.9. Is it right?
Yes, sir.
Yeah. So it will come out to be around 1.11.
Okay.
Yeah. So let's move on to the next question. So this is also a similar kind of question. Okay. I hope you will be able to solve this. So with some values are given. So we have a water flows at a velocity at 1 meter per second over a flat plate of length 0.6 meter. Consider two cases. One with the water temperature is approximately 300 Kelvin, while other water temperature is approximately 350 Kelvin. So the laminar and turbulent regimes experimentally results means in the turbulent and turbulent regime, the local heat transfer coefficients are found out experimentally, which is given as a function of x and its values, the constant values at this 300 and 350 Kelvin is also given. So we have to determine the average heat transfer coefficient over the plate for the two water temperatures. Okay, so what here it is missing is you may need the the properties of water. At 300 Kelvin, you can take density as meter cube, and viscosity 3 is 855 into 10 raised to minus 6 Newton second per meter square. And at 350 Kelvin, rho as 974 kilogram per meter cube, and mu as 365 into 10 raised to minus 6 Newton second per meter square. So now you can start solving.
Just show the statement. Excuse me, sir.
Can you repeat?
Sir, actually, the statement that you show me the full statement.
This one.
Yeah, yeah. Viscosity and or the kinematic viscosity, is it given? Okay.
Yeah, mu is given. I already specified. So first, what we have to find out?
First, we will be finding out the Reynolds number.
Yeah. So can you? So first we will take the case of at for 300 degrees, 300 Kelvin. Okay. So what is the Reynolds number? Rho VT or rho for flat plate, it is x by mu, right? So we have to find out the critical length, and we have to check whether the what is the flow regime of the plate. That is the first check we have to write. So the critical length is equal to Reynolds number critical times mu divided by rho u infinity. What is the critical Reynolds number for a flat plate?
So 5 into 10 to power 5.
Yeah, 5 into 10 to the power 5 into viscosity is given, density is given, and u infinity is 1. Can you find what is this critical value?
So 0.43.
Yeah. 0.43 meters, right? So which means that the plate is 1 meter long. So up to 0 to 0.43 meters, the flow is laminar, and after 0.43 meter, the flow is turbulent. Okay, so we have to accommodate for
But,
that.
but sir, first we have to calculate the Reynolds number, whether the flow is turbulent or laminar. Isn't it that first we will be checking whether
Yeah,
the,
that's what we are doing, right? First, we are checking the critical Reynolds number, and say, for example, if the critical Reynolds number was say 1.2.
but sir, you have not calculated the Reynolds number.
No, critical Reynolds
You
number
are
we already know, no? For the
where?
laminar to turbulent transition, it's 5 into 10 raised to 5.
Okay, okay.
I am calculating the critical length
But sir,
where the
in all the books, first they will be calculating the Reynolds number, and then they will be uh, finding whether the flow has entered the turbulent regime or not, and then they will be finding out. I don't know why they
yeah, I
are.
means I just bypass this. You can either do like that. First, you can check what is the for and over the entire length. You can check what is the Reynolds number. So you will get that it is above 5 into 10 raised to 5, right? So then you have to find out the critical Reynolds number. Okay, that way is the right way because I just skipped that step. First, you can check whether the entire regime or the what is the means or the length of the plate, whether it is laminar or it's a laminar and plus turbulent, by just putting the value of x is equal to L in the Reynolds number. Okay, so can you please check what is the Reynolds number if you put x is equal to L?
That means if I am putting 0.43, oh, that full length.
Yeah, full length. L is 1.
So what is the velocity?
1 meters per second. I think it will be anyway above 5 into 10 raised to 5.
So it is approximately 1.16 10 to power 6.
Yeah. So anyway, it is above the critical Reynolds number, right? So, so we have to first found, then we can confirm that there is a the over the length of the plate, both regimes exist, both laminar and turbulent. Next, we have to find out at what point this transition happens. That is what I did. Okay,
Sir,
at x
actually,
is equal.
sir, one more doubt. When we are
Hmm.
getting this Reynolds number is as that turbulent flow, then when we are finding out. So can it happen that there is no laminar flow available on the plate?
Yeah, it can happen when it is specified that the flow is always turbulent, because when in this question it is nothing specified, so you can make a flow turbulent at the beginning itself by using some methods, some tripping methods like that. If you use some methods, there will not be any laminar regime at all,
Okay.
but you have to artificially do that. For
So,
a normal flow, there will be always laminar transition turbulent.
okay, sir.
You can make this if you check the some standard textbooks like in Coopera and all. You can find these kind of questions where initially itself it is turbulent by using some tripping methods or like that. You can check with that kind of question. And if it is not specified, then you have to do like this. So here we found out that the critical length at which the laminar to turbulent transition happens is 0.43. So we have to, for average heat transfer coefficient, we have to consider both laminar and turbulent rate. So H bar is equal to 1 by L. So the heat transfer coefficient is different for both laminar and turbulent rate. So up to critical length, it is H laminar dx plus then from critical length to L, which is turbulent dx. Okay. So it is equal to 1 by L, 0 to critical length is 0.43. H laminar is C laminar at 300 times x raised to 0.5. So it is 395 x raised to minus 0.5 dx plus integral 0.43 to L. Turbulent, it is how much? C turbulent is, yeah, 2330 x raised to minus zero point 0.2, right? Yeah, it's to minus zero point 0.2 dx. So here L is equal to 1. So I'm writing as 1. Okay. So you can just calculate it. I hope you can do this integration. So if you integrate, you will get H bar is equal to 1620 watt per meter square Kelvin. Any doubt?
No, sir.
Yeah. So same at for 300 Kelvin also. Sorry, 350 Kelvin also. So first, if you go in your way, first calculate what is the Reynolds number at with these properties. You should check that the properties are changing. Okay, so the you can find out the Reynolds number, and the Reynolds number is it will be above for this question. It will be above the critical Reynolds number. So we have to find. So you can say that there is a laminar and a turbulent regime. Then you have to find out at what length this transition happens. So this transition is so 5 into 10 raised to 5 into 365 into 10 raised to minus 6. If you see, this will be at 0.19 meter. Okay. So at 0.19 meter, the laminar to turbulent happens. Next, now just the same thing 1 by L integral 0 to L h dx. So 1 by L integral 0 to XCR critical Reynolds number. C laminar is how much? 477 x raised to minus zero point 0.5 dx plus 360 integrals uh, XCR times L x raised to what is the minus zero point 0.2. Okay. So if you write this is 1 by L integral 0 to 0.19477 x raised to minus zero point 0.5 dx plus integral 0.19213600 x raised to minus zero point 0.2 dx. If you calculate this, you will get around 3710 watt per meter square Kelvin. So same procedures, only at two different temperatures. That's only the difference.
Sir, here when you are taking this average heat transfer coefficient, you are writing 1 over L 0 raised to 0 to L H dx. Why we
Yeah.
are not writing 1 by X?
No, in the previous question, it is asked at from 0 to a particular location x. Okay. So the x is it's not required that say for example this is a L. Okay, this is the plate. So its length is L. So I am considering a location at X from this leading edge. Okay. So I am calculating this much heat transfer coefficient only. This is H bar X. Okay. But in this case, I'm asked to find out the heat transfer coefficient over the entire length. That's why I'm taking L.
Okay, sir.
Okay. So this was a simple question. Now we'll move on to the next question. So you don't these options are not. So a circular gas jet at the infinity is directed normal to a circular plate that has radius r0 and is maintained at a uniform temperature Ts. Gla- Gas flows over the plate is axisymmetric, causing the local heat transfer coefficient to have a radial dependence of the form A plus B r raised to n, where A, B, n are constant. Determine the rate of heat transfer to the plate. This is the question. I will give you 2 minutes. So excuse me for 2 minutes. I will come back within within 2 minutes. Okay.
Okay, sir.
Yeah. In in this question, so have you got the answer?
I have that got it in the that in a form of expression. I integrated it.
Yeah, let's see. So this is our plate, and we have a axisymmetric jet that is coming. Okay, so I am taking it R. So at any location R, the heat transfer coefficient is given A plus B R raised to N. Okay, so I am taking an elemental strip at a location R. Okay, so of this of this plate. So this is some Ts, and we have T infinity flowing R at a distance, and the is dr, and the Q convection dq is given. So dq convection is equal to hr 2 pi r dr, the area of heat transfer, times Ts minus T infinity, or here T infinity is more, so T infinity minus Ts. Is this the first expression?
But sir, I put here pi r square.
Why pi r square? Because if you see from the top, okay, so this is our uh, disk. So we should take the heat transfer area, right? So the heat is transferring. So at a, I am right. This is at a distance r. This is our elemental strip at a distance r. So this is the dr. This is my elemental strip. If you see from the bottom, sorry, from the top, this is dr. So the heat transfer area is how much? This is the heat transfer area, right? Which is 2 pi r dr. I hope you now you understood.
Yes, sir.
Yeah. So you have for convection, you should take the heat transfer area. So now we are integrating it. Integral 0 to r naught, which is the radius. Is the it's what the radius of the disk, hr 2 pi r dr, ts t infinity minus ts. So which is 2 pi is constant, t infinity minus ts is constant, equals 0 to r naught a plus b r raised to n dr into r. So, okay, sorry, one r is also there. B r raised to n plus 1 times dr. Okay, so now if you integrate a r square by 2 plus b r raised to n plus 2 by n plus 2 r naught to 0. So the q total convection is 2 pi t infinity minus ts a r 0 square by 2 plus b r 0 n plus 2 by n plus 2. Okay, so it was, so the only thing is which is was here up to here. You need to look. So rest is just integration part. So this question is almost similar to the first question. Okay, so can you please try this? So we have air at a free stream, temperature of T infinity is equal to 20 degrees Celsius, parallel flow. Otherwise, this you can try it as a homework, okay? Because this is a similar kind of question, that's why. So we will move on to this question. So heat is being transferred by convection from water, which is at 48 degrees Celsius, to a glass whose surface that is exposed to water is 40 degrees. Means thermal conductivity of the water is given, the thermal conductivity of the glass is given, and the spatial gradient of temperature in the water at water glass interface is also given, and we have to find out the heat transfer coefficient.
What will be putting balance, heat balance by conduction equal to convection?
What the answer? So we have a interface. This is glass. Okay, this is glass and this is water. The water is flowing at 48 degrees Celsius and the glass is at 40 degrees Celsius. The surface of the glass is at 40 degrees Celsius. And the temperature gradient, that is dt by dy, in the water at the water glass interface, which means y is equal to 0 is given as 1 into 10 raised to 4. Just you need to equate, that's all, right? So what is q? H is equal to minus k water dt by dy at y is equal to 0 divided by T infinity, sorry, T wall minus T glass. Okay, what is this answer? Water is given thermal conductivity. How much of the thermal conductivity of the glass? Water. 0.6 into 1 into 10 raised to 4. What is this answer? It is around 6,000 divided by 8. Will
So
be,
750.
yeah,
Uh, Sir, I have a doubt
yeah,
in this question.
yeah.
That nowhere it is written that the water is moving.
No, it's already mentioned that the heat is transferred by convection from water. It's not
Can't the
mentioned
water be
that the
still?
water is still also.
So water can be still also.
No, it is already moved. Otherwise, it should be natural convection. Anyway, if even though if it is natural convection, some current will be formed.
Yes.
Eh, Then also this expression is valid.
Sir, can't we equate that K Kf dt by dy is equal to H Ts minus T infinity?
Okay.
K dt by dy.
Ah,
But then
that
the
is what I did. If you take this is the equation.
but I didn't get the answer. But I do. Okay.
You may have put the thermal conductivity of glass.
Okay, I got the answer. Okay, I did the calculations wrong. Otherwise, I would have got the answer. Okay, sir.
Okay,
Thank you.
yeah, fine. So this is a question, so you can just answer it. That's all, because this is already discussed in the class. So we have a flow or a flat plate where the temperature of the fluid and the plate are different. The heat transfer at the leading edge will be dash, whether it is larger, lower, or same than the trailing edge. So this is a flow or a flat plate. Which is leading edge? This one or this one? The left side one or right side one is the leading edge.
So left side we take the
Yeah, the
leading
flow
edge.
is from here.
Yeah, but otherwise the direction of the flow will decide which is the
Yeah,
leading edge.
means this is why I given. So if the flow is from left to right, so which is leading and which is trailing?
Okay, so here the left is leading.
Yeah. So the edge that is encounters the flow first is the leading edge, and the other end is known as the trailing edge. Okay. So if we go the boundary layer, so what is this answer? So heat transfer coefficient or heat transfer will
Will be
be
lower
higher.
than because the turbulence will be after certain length.
No, no. You assume that there is no turbulence. The flow is laminar, entirely laminar till trailing edge. Assume flow is laminar.
Then it will be same.
How? Can you explain?
because when it is steady state,
Mm.
uh, when it is steady states, and then there will be no change of velocity, and
Uh,
our convection coefficient is a function of velocity.
what about temperature? What is our expression? H is equal to minus kf dot t by dou y at y is equal to 0 by ts minus t infinity. Okay. So this kf is same. Ts minus t infinity is also constant. So the h depends on what? The temperature gradient at the at y is equal to 0. If this is x and y. Am I right?
So you are right, but when we are talking only within the boundary layer,
Yeah, I am talking about the boundary layer only.
okay, yes, sir.
Okay. So, so I'm assuming that Ts is greater Ts is greater than T infinity. Okay. So the temperature profile will be something like this. So one, two, three. So which gradient will be higher, which gradient will be lower? Means dou t by dou y or dt by dy at one location one, dt by dy at location two, dt by dy at location three. How to connect this?
Sir, this gradient is decreasing.
Gradient is decreasing. So the higher gradient will be for one, then followed by two, then three. Okay. Then how the heat transfer coefficient affects? Because heat transfer coefficient is a direct function of gradient. So the heat transfer coefficient will be also
Decreasing
decreasing. So heat transfer at the near to the trailing edge, leading edge
is
is greater
maximum.
or
Is
greater
is
greater than the
is maximum, I think.
yeah maximum. Which that depends on whether the turbulent is also there. Because in turbulent case the heat transfer coefficient can be more. So that's why I specify limit to lambda. So if you see from there will be a jump in the turbulent regime. So that we will study in the due course of this uh, in the due course. So otherwise we can just refer to some textbook also. So okay. So now let's come to the end of this session. So I hope this session was helpful to you, which helps you to solve some problems related to this course. So, uh, so are you helpful with this session?
Yes,
I
sir.
want, yeah. So okay, then we will meet in the next week, next Monday, the same time with the week four content. So till then, have a nice week ahead. Thanks for joining. Thank you.
Okay, sir. Thank you.
Thanks. Thank you.